I don't want to take too much time with questions and stuff before I get into new stuff, because I just want to get to a point today where you can do more problems. We're sort of at the end of the problems you can do right now. But does anyone have any question about the test first? Or homework? Okay, that's what I like to hear. That's what I was hoping you would say. All right, so for stresses and beams, let me say that first. We know that the total stress tensor is equal to the stress tensor that you'd get just from the tension, ignoring all the other stuff, plus the stress tensor that you get just from the bending moment, ignoring all the other stuff, plus the stress tensor that you get just from the shear force, plus the stress tensor that you get just from the torque. And right now we've talked about this one and talked about this one. So the next thing we have to talk about is how to calculate the stress due to a shear force. And once we get that, there are a lot of beam problems that we can solve. You know, there's just a lot of beam problems that don't have any torsion. There are no beam well, I shouldn't say, there are ways to do it, but for the most part, if you have bending in a beam, you also have shear force in the beam. So we can't do any complete problems yet with these two for the most part, but we will be able to once we talk about how to calculate the stress due to shear force. And then torsion, that appears in some problems, but not all. Okay, so stress is due to shear force. So we didn't have much in the way of requirements for the beam when we were talking about the stresses due to tension compression. We had a couple of requirements when we're talking about stresses due to bending. They had to be pretty straight, more or less straight, and they had to be prismatic. And then they had to be symmetric about the vertical axis. But there are a lot of beam types that fit into that categories. With shear forces, we have a lot more stringent requirements. So the requirements for shear force are much more limiting. That's not a word. We can only calculate the stress due to shear force for two cross-sectional shapes. The first is a rectangle. And the results are more accurate when the height is bigger than the base, or the width. Let's call it the width. No, let's call it base, because that's going to come up later. So a rectangular cross-section like this, where this is the neutral axis, is good. A cross-section like this the results are bad. So we don't want to use this to do calculations. Yep.
Is good and bad, like in terms of accuracy?
Accuracy, yeah. Because all of these, I'm not going into the derivations of how, but these are all just mathematical derivations made from assumptions that you see in measurements. And so as you get to having a height that's smaller than the base, the assumptions that we're making to do this mathematical derivation, you don't see, you know. And so it's a bad assumption and your results are bad. No, it's not, but that is the distinction we're making here. The bending calculator thing was talking about when the area moment of inertia is big and when it's small. So that was talking about how well that shape resists bending in those two orientations. So when it's vertical, it's really hard to bend it. In an extreme example, like, you know, think of a piece of paper. Like, if you try to bend it like this, it folds. But you can imagine it would be very hard to bend this sheet of paper this way. Like this, you know, gravity is more than enough to bend it. Okay, so that's the first shape we can deal with. The second shape is circular. And even then, we can only calculate the stresses along the neutral axis. So you might ask yourself if there's even any reason to do this calculation for circular cross sections if we know so little about it. Well, it turns out that the neutral axis is always where the stress is the highest due to shear force. So the good news, at least, is that the stress due to shear force is maximum on the neutral axis. Okay, so one thing to notice is here you go. Remember that the stress due to bending is greatest at the top and bottom of the cross section. And it's 0 at the neutral axis. The stress due to shear force is greatest at the neutral axis. And 0 at the top and bottom. Of the cross section. Okay, so before we get into the calculation of the stress due to shear force, we need one mathematical definition. one mathematical preliminary. And that is this thing called, we're going to call it Q. I suppose if you had to give it a name, you would call it the, I've never really heard anyone call it this, but I suppose it would be the first moment of the area about the neutral axis. And the best way to give the definition is just to draw a picture. So if this is the cross section, and this is the neutral axis. Remember, the neutral axis has to go through the centroid. And this line y1 is where you're calculating the stress. So this is where you want to calculate the stress due to the shear force. Calculate the area above that line. Bless you. And that's equal to A1. And now take the centroid of that shape, the dotted region, centroid of the shaded region. And calculate the distance from the neutral axis to this centroid. So I'll call that D. I guess I'll call it D1. I put ones in everything else for some reason. Then the value of Q is equal to the area of the shaded region times that distance D1. Here's sort of a cool fact that might occasionally be useful. Okay, I'm sort of hedging on it being a fact. We'll call it a cool factoid, something similar to a fact. And that is that if you calculate Q using that shaded area above the line Y1, it's the same thing that you would get calculating Q using the area and the distance to the centroid below Y1. So you can always do it either way. You know, imagine everything that's white here now being the shaded region. And then that white area has a centroid. Calculate the distance from the neutral axis to the centroid of the white region. You get the same number. Sort of a surprising fact, but it just has to do with the definition of the centroid. If you sort of untangle all the calculations of the centroid, you can prove that that has to be the case.
The whole area below the neutral axis?
Not necessarily, not below the neutral axis, below Y1.
Below. Oh.
You see what I mean? So like in this case,
Yes.
what we'd have here is that white area below Y1 is a bigger area, but the centroid is much closer to the neutral axis. And those, the way it works is that those offset each other in such a way that it's always the same. You can also see, I mentioned that the stress due to the shear force is always equal to 0 at the top and the bottom. Well, if you think of what that, think of what that area means. If your y1, where you want to calculate the stress, is at the top, there's no area above it, and so you get 0 for Q. Okay, so let's do an example of this calculation. So let's say we have a cross section that's 1 meter high, has a width of half a meter. And we want to calculate Q at this line. So this is our y1, and it's 0.8 meters from the bottom. So what's Q for the line y1? Well, the centroid is here, and so this is the neutral axis. The area above y1 is this. So A1 is equal to 0.2 times 0.5. Bless you. So that's 0.01. No, 0.1. The centroid of this area is here. And so this is D1. And so D1 is equal to, well, it's 0.3 to get from the neutral axis to here. Another 0.1 to get from Y1 to the centroid of that shaded region.
0.01 for the area?
1/5 of 0.5 is 0.1. That's my argument. Okay, so D1 is equal to 0.3. That's the distance from the neutral axis to Y1. And then plus another 0.1 to get from Y1 to the centroid of the shaded region. So 0.4. And that's meters. And so Q is equal to the area times that distance, so 0.04, and the units are meters cubed. Any questions about that? Okay, so now I'm going to draw a picture that hopefully sort of clarifies what's happening with the stresses. I'm a little nervous about this, how this will go. So this is visualizing the stress due to the shear force. All right, so let's say this is the end of the beam. No, don't do it like that. Do it like this. Sorry about that. for everyone ruining their notebooks right now. Okay, this will be better. So there's the end. And the shear force is acting like this. And we're calculating shear stresses along a line like this. And so let's pick out one stress element and think about what that looks like. Okay. So that shear force acting down makes sense that that would cause a stress like this. If your coordinate system has the x-axis this way, the y-axis this way, and the z-axis this way, that's what we're always going to use, then what element would this red stress be? That's xy, yep. Stress xy. Or you can write it like this. And by the requirements of a stress element, we also have an equal and opposite stress like this. Okay, so those are the elements of stress that are produced by the shear force. So the stress due to the shear force only has non-zero xy shear stress. And the value of that shear stress, tau xy, is equal to negative shear force times Q divided by IB. You can trust the sign on this one, so you don't have to think physically about the directions. But if you think physically about the directions, you know, if you have a positive value of the shear force, it means from this picture you can see that that's a negative xy shear stress. And if you have a upward shear force, that's a negative V, and that would give you a positive value of the xy shear stress. But you can trust this sign. I is the area moment of inertia, the same one that we used for the bending, for the stress due to bending. And B is the width of the base where you're calculating that shear stress. Yes, that is the width along the z-axis. That's right. Okay, well, with that, we can now calculate complete stress tensors for certain beam problems. You know, remember, this isn't true generally for beams, but we can do it for some beam problems. with no torque. No torsion. Okay, so let's do an example. So let's say we have a cantilever beam. It's 2 meters long. The mass of the beam is 100 kilograms. You know what's funny? I hadn't thought of this. This doesn't change anything about the calculations that we've been doing. But I have all these problems where I give dimensions of the beam and then give a weight. And the weight is like totally out of the realm of possibility for densities of materials. I've never like multiplied it out to a volume, and yeah, this is one of those. Okay, well, let's say we're doing this calculation on a very large planet. Okay, so the weight is higher than you would expect. Okay, the cross section looks like this. So let's say it's 10 centimeters tall, 0.1 meters. And the width is 2 centimeters. And we want to calculate the stress tensor. So if this is the neutral axis, we want to calculate the stress tensor on a line halfway between the neutral axis and the top. Okay, so we want to calculate the stress tensor here, and we also need to know in the x-y plane where we're looking, so we want to do that at the midpoint, let's say. All right, well, if we're not going to calculate these stresses as functions of x, we can just do our cut at the dotted line, the one place we care about. So we'll just cut at the dotted line. It's just like kindergarten again. Except for the part where you do all the engineering calculations. Okay, so there's the part that we care about. The load's acting. There's some weight. We're looking at half of the beam, so that means half the weight is acting at the midpoint of this. It's 100 kilograms, so 50 kilograms of weight is acting on our chosen piece. So that's 490.5 newtons. And then we have T, V, M. We would have fancy T, but there's no torsion in this problem. So Newton's second law says 0, negative 490.5, plus T, negative V, is equal to zeros. So T is equal to 0. V is equal to negative 490.5. And then the moment equation, this is the Z moment. If our about point is at the left, like always, what's the moment arm of this 490.5? The whole thing is 1. So this is 0.5, because we're just looking at the left half. So 0.5 times 490.5, and is that clockwise or counterclockwise? That's you. clockwise, so that's negative. And then we have plus m minus Vx. The length is 2 meters. The length of our piece is 1 meter. So m is equal to 245.25 minus, oh, I said x, but we know what that x is. That's just out of habit. So the moment arm for V is 1. So this is minus 490.5 times 1. So negative 245.25. So why doesn't it look like dm dx is equal to v?
Isn't V negative 490?
Yep.
So negative 490 minus, is it not negative? Just good enough on the top.
I think that should be right. But this is just a general thing with calculus that can throw you off in engineering problems a lot. Like a lot of times you're doing calculations at a single point or a single instant in time or whatever. And so if you're just looking at one spot on a graph, you don't have any information that you can use for derivatives. You know? So if we had calculated this as a function of x, so we had all the information about what this curve does as x varies, then you could take that derivative and it would be equal to v. If we're just looking at a point, it's kind of, the question is like, here's a point on a graph, what's its slope? It doesn't, that question doesn't make any sense, you know. So if you're just looking at a point like this, you can't use those derivative checks. Okay, so now we have the internal loads, and we're going to do the stress calculations. The total stress is equal to the stress due to tension plus the stress due to bending moment plus the stress due to the shear force plus the stress due to the torsion. This one's equal to 0 because tension is equal to 0. This one's equal to 0 because there's no torque. And so we just have to deal with the bending moment and the shear force. For the stress due to the bending moment, the XX stress is equal to negative my over I. So we have to calculate that I value. I is equal to 1/12 times the base times the height cubed. The base was 0.02, the height is 0.1. And so you get 1.6 repeating times 10 to the minus 6 meters to the fourth. And so the XX stress is equal to negative bending moment. So the bending moment is negative 245.25. Y is the height above the neutral axis. So what's Y for this line that we're looking at? 0.025. and it's positive because it's above. Then we'll divide that by 1.6 repeating times 10 to the minus 6, and you get an XX stress of 3.68 times 10 to the 6 pascals. Yep. Y is, so remember that the stress due to bending varies as you go up and down on the cross section. So that Y depends on what point you're looking at the stress for. It doesn't, that's not just asking you the height of the beam. Okay? So since this is where we're looking for the stress, the value, the distance we want is from the neutral axis to the point that we want. Okay, so the stress tensor due to bending is 3.68 times 10 to the 6, zeros everywhere else. And now we'll do the stress due to the shear force. Tau xy is equal to negative VQ over IB. We already have I. We had to calculate that for the bending moment. We have to calculate Q. So Q is equal to the area above this line that we care about times the distance from the neutral axis to the centroid of that area that we just calculated. So what's the area of that region? The area of this is 0.02 times 0.025. And then what's the distance from the neutral axis to the centroid of that region? So 0.25 to get here, plus another 0.0125, so 0.0375, I think, right? And so Q is equal to 1.875 times 10 to the minus 5. And that's meters cubed. So tau xy is equal to negative of whatever our shear force was, negative 490.5, times Q, 1.875 times 10 to the minus 5, divided by I, which was 1.6 repeating times 10 to the minus 6, times the width in the z direction of the cross-section at the line that we care about, so that's 0.02. And if you calculate that, you get 275,906 pascals. So the stress tensor due to the shear force is 0. I'll write it as 0.276 times 10 to the 6, 0, 0.276 times 10 to the 6, zeros everywhere else. And so then to add those together, you just add up like elements. You know, add any xx's together, any xy's together, xz's together. So the stress tensor is equal to the stress tensor due to bending moment plus the stress tensor due to the shear force. And that is 3.68 times 10 to the 6, 0.276 times 10 to the 6, 0, 0.276 times 10 to the 6, 0, 0, 0, 0, 0. For the purposes of figuring out, if you imagine that this is a brittle material and fracture is going to be determined by the maximum shear stress, how would you find the maximum shear stress that's happening at this point?
Don't we find our principles?
Yep, exactly.
And go from there?
Yep, find the principal stress, and then you can just use the formula, or if you want the stress tensor, you can do the 45-degree rotation. So does somebody who has that in their calculator, can someone punch that in and tell me what the principal stresses are?
Our eigenvalues are 3.7 e to the 6,
Okay.
negative 20584.9, and 0.
2.584.
2.0585.
2?
Negative 2.
Or times something.
Oh, wait. 20585. Nope. Just no there.
Okay, so 2.
10 to the 1, 2, 3, 4.
Oh, 4. Okay. And then 0.
Yes, sir.
Okay, so there is a principal stress tensor. So you can put them in any order. It just refers to a different coordinate system, how you move it around. And then the maximum shear stress is the max of these, 3.70 times 10 to the 6, minus the min, divided by 2, which is basically just half of 3.70. But what do you get at? What's 3.7 times 10 to the 6 plus 2.06 times 10 to the 4 divided by 2?
E to the 6.
1.86 times 10 to the 6 pascals. So compare that to the shear stress that that material is capable of withstanding, and that would give you a sense of how much risk you're in for this fracturing at that particular point. Because remember, we just did this calculation for points along that one line. Any questions about that? Okay, well, let's take a 10-minute break, come back at 2:02, and we'll do another example, and then we'll start the quiz about 2:30. Anybody have any questions from that last example? Okay, so that one had a rectangular cross-section. We can do one other type of cross-sectional shape, circle, but then we can only do it along the neutral axis. For circular cross-sections, we can only do stress calculations along the neutral axis. And because of that, the value of Q is always the same, just depends on the radius of the circle, because you're not going up or down at all, you know. And the value of B is always the same, it's just the diameter of the circle. So if tau xy is equal to negative VQ over IB, we can just always express we can give a simple expression for this along the neutral axis, the only place we care about it, just in terms of the radius. So I, for a circle, is equal to pi r to the 4th over 4. B, for a circle at the neutral axis, is equal to 2r. Q, for a circle at the neutral axis, well, the area above the neutral axis is just half of the circle, so pi r squared over 2. The distance from the neutral axis to the centroid of that area above is that we have a formula for that. It's 4r over 3 pi. So the pi's cancel out. The 2 cancels and makes the one in the numerator a 2. And so you get 2r cubed over 3. And so the xy stress is equal to negative shear force times 2r cubed over 3, that's V times Q, divided by IB, so pi r to the 4th with a 4 in the numerator. B is 2r, then a whole bunch of stuff cancels. That 2, this and all of that. And so you get negative 4v over 3 pi r squared, something like that. I don't really know if that's true or not, but I know you can come up with a formula like that. I don't have it written down here. View that with some skepticism, but you can do that calculation in that way. Here are the things that I'll give you on tests. Or something like it. So I'll give you the formula for the area moment of inertia and this formula for Q for a circle. Okay, so let's do an example with a circular cross-section. So let's say we have a cantilever on the left. Rats! Let's say it's 1 meter long. This is another. Now that when I see these, I'm like so embarrassed now. This is another one that would have to be made out of like neutron star. But there's a tension of 20,000 newtons that way. The mass is 1,000 kilograms. The cross section has a radius of 0.2 meters. And we want to know what's the stress tensor for points along the neutral axis. And I have to give a point along the x-axis too. I guess I chose the midpoint again. So at the beam's midpoint. So what's the first thing we have to do? Yeah, we have to figure out those external loads. So I'll draw a free body diagram of the whole thing. We have a downward force of 1,000 times 9.81, so 9810. We have a horizontal force of 1,000 to the right, on the right side. And then over here, we have a reaction force and a couple due to the fixed joint. Yes. $20,000. Okay, so Newton's second law says RAX, RAY plus 0, negative 9810, plus this force is in the positive x direction, 20,000, 0 is equal to zeros. So the force vector RA is equal to negative 20,000, positive 9810. The moment equation, let's calculate all this about the left endpoint. There's no moment produced by R, but we do add the MR. Then the 9810, what's its moment arm? 0.5. And is that positive or negative? Negative. And then is there a moment produced by the 20,000? Nope. So MR is equal to 4905. And now we can do our cut. So we're going to do our cut at x equals 0.5. We have our force vector that we just calculated at the left, negative 20,000, positive 9810. And our couple of 4905. And then we have a weight force. So you could do it as a distributed load. In this case, the distributed load would be 9810 divided by a length of 1. So 9810 newtons per meter, and you could go that way. Or you could just recognize that we're looking at half the beam, so we're going to be looking at half the weight. So we have a downward force of 4905 acting at the beam's midpoint. And then we have T, V, M. So Newton's second law says negative 20,000, positive 9810. Plus 0, negative 4905. Plus T, negative V is zeros. So T is equal to positive 20,000. V is equal to positive 4905. And then the moment equation, our about point is the left end. So the negative 20,000, positive 9810 doesn't produce any moment, but the couple of 4905 does, so positive 4905. Then what's the moment arm of the 4905 force? This whole thing is 0.5 meters, so 0.25. So 0.25 times 4905, and is that positive or negative? Negative plus m minus Vx is equal to 0. And x is 0.5. Keep doing that. So we have m is equal to negative 4905 plus 0.25 times 4905 plus 0.5 times this is 2452.5. And so what do you get for m? $136? Oh, 1226. I've seen that number before. And that's Newton meters. These are newtons. Thank you. Okay. So now we can calculate the stress tensor. The total stress tensor is the stress tensor due to tension plus the stress tensor due to bending plus the stress tensor due to the shear force plus the stress tensor due to torsion. There's no torsion, so that goes away. We're at the neutral axis, so that goes away. So first, the stress tensor due to tension. So the XX stress is equal to tension divided by the cross-sectional area. The tension was positive 20,000. The area is pi r squared, so pi times 0.2 squared. And what do you get for that? Okay, and that's Pascal's. So the stress tensor due to tension is 1.6 times 10 to the 5th, zeros everywhere else. And now we have to do the one for the shear force. So B is equal to 2 times the radius, so 0.4. Q is equal to 2/3 times the radius to the third. Can someone calculate that one? 0.0053? 0.0053. I is equal to pi times 0.2 to the 4th over 4. What do you get for that? Zero zero 125. Our shear force is 4905. So tau xy is equal to negative 4905 times 0.0053 divided by 0.00125 divided by 0.4. And what do you get for that? 5.2 times 10 to the 4th. So the stress due to shear force, and it's negative, right? So the stress due to shear force is 0, negative 5.2 times 10 to the 4th, 0, negative 5.2 times 10 to the 4th, zeros everywhere else. And so the total stress tensor along the neutral axis at the midpoint of the beam is the stress due to tension plus the stress due to shear force. So that's 1.6 times 10 to the 5th minus 5.2 times 10 to the 4th, 0, negative 5.2 times 10 to the fourth, 0, 0, 0, 0, 0 pascals. And those are pretty small stresses, so there aren't too many materials that would have any trouble withstanding that. But if you wanted to calculate the max shear stress, take the principal stresses and then use the formula to calculate the max shear. Any questions? Yep.
For this one, I know we're on the neutral axis because we're doing a circle.
Yeah.
But why again do we not include the bending moment?
Yeah, because remember the bending moment formula is negative my over I, and that y is the distance from the neutral axis to the point you're looking at. So if you're on the neutral axis, it's the stress is 0. And also, if you think of the definition of the neutral axis, it's the line along which the length doesn't change, so you're not going to have any stress. So those are sort of the two ways to think about it. Any other questions? Okay, let's do the quiz.